Welcome to the PLodicy YouTube channel. I'm Robert Smarts. I've had a long interest in programming languages, and so I thought I'd make some videos about my programming language Odyssey, hence the title, and particularly about the resulting design decisions, which I think should be of general interest. So I started out programming in assembly language long ago, and back then there was little else for serious programming. That's why Don Knuth's magnum opus on algorithms uses his artificial assembly language. So yes, we want our high-level languages to make efficient use of the target machine, but this can and should be kept separate from the properties which define a type. So allowing multiple implementations for the same type is tricky, but I think it should be done without the need in most situations for the programmer to have to get involved. I have some ideas on how to do this, but mostly I won't be talking about this, at least in early videos. So in the early high-level languages like Fortran and Algol 60, identifiers had no fixed meaning. They were just envisaged as things that changed during the running of the program. This was different from assembly language, which is what I'd started on, where identifiers always stood for constants. Now that constant might be a memory address, and the contents of the memory might change, but we never in assembly language regarded that as a change in the identifier itself. But then along came Algol 68, and in Algol 68, identifiers stand for constants, even if that constant thing is effectively a memory location. So it was a return to assembly language. Now, Algol 68 had some significant problems, which I might talk about one day, but giving identifiers a constant meaning was not one of them. So one of my objectives is to make sure that every identifier has some fixed meaning. So what I didn't know at the time was that having identifiers with a constant meaning was an essential step to supporting functional programming, which I didn't at that stage know about. And that's certainly one of the things which I think is important. It's important that we support functional programming style, also some of logic programming, perhaps not backtracking, but as much as possible of a program should be written in a style that uses pure functions with no time-dependent semantics, so that same input always leads to the same output. Well, meanwhile, object-oriented programming arrived in the form of Stimulus 67, which added object-oriented and concurrency capabilities to Algol 60. And it turned out that the class hierarchy was extremely useful in organizing your program. But with everything changeable, OO made programs even harder to understand and get right. I think we can get this done right by having subtyping which fits with the way we think, and place types in a coherent type hierarchy in a way that makes operations and type conversions behave sensibly. And I'm certainly planning to spend a lot of time on that. I experimented with Erlang when it came along, and I really like the idea of concurrency-oriented programming. I'm not sure that it has to actually be in the programming language itself. It sounds more like a library thing. And then really liked the Mercury programming language, which is from the University of Melbourne in Australia. And it introduced me to the idea of procedures that can run in different ways depending on which inputs are known. But it does it in a way that looked more like Prolog, and I feel that it can be done in a way that looks more like ordinary mathematics and closer to ordinary programming, so that we can just write C equals A plus B instead of having, as in Mercury, add bracket A comma B comma C. So this idea of bidirectional execution is closely related to bidirectional type checking. At this stage in my programming language odyssey, a miracle arrived. I was very excited by the idea of incorporating mathematics more naturally into programming, and this was based on the observation that proofs are programs, propositions are types, and the key to making all this work was dependent types and proposition types. But I never really got comfortable with the systems that were created for this, like the proof environments. I wanted something that looked more like normal mathematics and more like the sort of programming languages I knew. So eventually I bit the bullet and incorporated these things into my programming language design, which I'd tinkered with for years. And the miracle was this, that programming language design suddenly becomes a whole lot easier. Because without this, when the programming language designer has to decide what things he can actually make work, that he can make the compiler understand. Whereas this allows you for the programmer to tell the compiler how to understand things. And so the library writer and the end programmer can tell the compiler how to make the deductions to make features work. And suddenly programming language design becomes a lot easier, of course. These programs are to some extent harder to write, but that's okay. So that's the main thing I'll be talking about, because it's certainly been a revelation for me. Well, that's all, and I'll hopefully come up with the real videos starting soon. See you then.